Yeah, good afternoon, all of you. Now I'm going to start the seventh topic, non-compartmental analysis. Non-compartmental analysis. For what? For PK parameters. So you want to analyzing the pharmacokinetic properties of a drug by three different ways. First one is compartmental analysis, right? And the second one is non-compartmental analysis. Then the third one is physiological models. So you want to analyzing the pharmacokinetic data for a drug through three different ways. Okay, so this introduction might be happened in the second unit, that is introduction to pharmacokinetics. Have you remembered that we have three different methods to analyze the pharmacokinetic data of a drug? First one is compartmental analysis. So in this compartmental analysis, we already studied about the one compartmental model. So you have multi-compartment model also under compartmental analysis. This is under fourth multi-compartment. Okay, I will tell you this later. And then the next one is non-compartmental analysis. So that is under your seventh unit. So what do you mean by non-compartmental? The name is indicating that it is not following any compartmental model. That means model compartment independent kinetics disease. That's why the name is called as non-compartmental analysis. So in this non-compartmental pharmacokinetics analysis, you are going to read about the statistical movement theory and mean residence time. MRT stands for mean residence time for various compartment models. So that means it includes IV bolus and it includes multi compartments. Okay, this is by one compartment open model. So here various means you have only three different models are there. So for these three different models you are going to read this MRT separately, mean residence time. So and the third one is physiological pharmacokinetic model. These three parts will comes under non-compartmental pharmacokinetics analysis. And one more important thing, there is a relationship between the statistical movement theory and the MRT. So in the classes, we are going to read these two combinedly. Don't get confused. So in your exam point of view, whenever they will ask to write you about the statistical movement theory, which includes MRT also. So mean residence time of a drug. Okay, these three parts will comes under non-compartmental pharmacokinetic analysis. So what do you mean by non-compartmental analysis? This is also called as model independent. That means it doesn't follows any model. That means one compartment or multi compartments. It doesn't assume like that. Does not require the assumption of specific compartment models, but it can be dependent on the assumption that the drugs or metabolites follow the linear kinetics. So in case of one compartment, you can assume our body as a single uniform compartment, right? So in this one compartment, we assume our body as a single uniform compartment. Then it will follows one compartment model through IV bolus or IV infusion, right? So these types of kinetics we studied. So when you want to administer your drug through IV bolus or IV infusion, when it will follows one compartment open model, here we calculated about elimination rate constant, right? And T half and the clearance, we already know about all these terms. So these will be comes under one compartment open model. In case of two compartment open model, or multi-compartment open model, we are going to calculate all these pharmacokinetics parameter on the basis of that particular model. So in case of this non-compartmental analysis, this is not at all depending upon any model like 1 or 2 or 3. So it is absolutely following the metabolites, those who are following the linear pharmacokinetics. That means the relationship between the plasma drug concentration and the time should be linear. On this basis, we are going to analyze the pharmacokinetic data for our drug. The non-compartmental approach for data analysis does not require any specific compartment model and can be applied to virtually any pharmacokinetic data we can be applied. There are various non-compartmental approaches including statistical movement analysis and system analysis or the non-compartmental recirculatory model. The main purpose of this non-compartmental approach is to estimate various pharmacokinetics. So in one compartment open model, we estimated elimination rate constant, clearance and elimination half-life. In the same manner, here we are going to estimate the systemic clearance of the drug, volume of distribution, the systemic clearance and volume of distribution of the drug at the steady state. And then mean residence time, this is what the MRT, mean residence time, and the bioavailability. Okay, without assuming or understanding any structural or mechanistic properties of the drug. So here we are taking only our uh, drug which is available in our body, which will follows non-compartment model. It is not depending upon any model. So we are not taking consideration into any structural or mechanistic properties of the drug. Okay, we can directly calculate the pharmacokinetic parameters on the basis of the statistical movement analysis and the mean residence time. The residence time is nothing but the transit time of the drug molecules in our body. So how much time they spend in our body, that is nothing but the transit or the residence time of the drug particles in our body. That should be taken into consideration to calculate the pharmacokinetics data here in non-compartmental analysis. So how it will be? First one is statistical movement theory. These three topics are very important in this unit. The statistical movement theory provides a unique way to study time-related changes in the macroscopic events. So here you need to remember one thing, how the behavior of the drug in our body. Drug is consisting of number of molecules or particles, right? So once they entered into our body, how they are acting on the basis of the time. So here we need to take time into consideration. The related changes in the macroscopic event. So what do you mean by macroscopic event? It is the event brought about by the constitutive elements involved. Don't get confused here in the sense of drug particles. Drug particles. So for example, in a chemical processing, a dose of tracer molecules. In a chemical processing, suppose it is a reactor tank. You just assume it as it is a reactor tank. So through this tank you have to introduce particular dose of tracer molecules. So here your tracer molecules are nothing but the drug molecules or drug moiety. Okay, drug molecules. So when you want to introduce this particular dose of the drug molecules into the reactor tanker. So I'm telling you about the molecules. Okay, so this may contains more number of molecules, that is approximately assume that 20 to 30 particles should be present. Okay, so once you injected the dose molecules into this reactor tank, this is called reactor tank. So you need to calculate the residence time of the molecules. You need to calculate the residence time. So that is RT, that is denoted by RT. So we cannot calculate the individual particle residence time. That means we cannot assume that only one particle will stay up to 10 minutes or 20 minutes. We can't take into consideration because the powder molecule, the drug molecule will have more than 10 number of particles. So we cannot assume the particular particle residence time in our body, that is nothing but our tank. So that's why here we need to take the mean of this residence time particles. Okay, so the mean residence time is denoted U as MRT. In this lesson, the mean residence time, that is MRT, you are going to calculate that. This MRT will gives you the average time of the particles spent in this reactor tanker. So either of your particles may have more than 10 or 20 or 30. So you can take the average, then that is called as mean residence time. So you already know that 10, 20, 30, 40 minutes are the timings for four different particles. Suppose. So you need to calculate the average time first. So how you need to calculate? Total 10 plus 20 plus 30 plus 40 by 1, 2, 3, 4. So you will get one X number. So then this will be considered as average. So for that, same like that, you can estimate the mean residence time for the molecules. Those are tracer molecules which are injected into the reactor tank at a particular dose. That is denoted by our mean residence time. So this is what the sentence meaning exactly. See, the constitutive elements in this example are the tracer molecules and the macroscopic events. The residence times shared by group of tracer molecules, we are going to calculate it here. Each tracer molecule is well mixed and distributes non-interactively and randomly in the tank. So I already told you here there is a involvement of tracer molecules. So how the tracer molecules movement will be? Definitely those have some randomized movement. Those are not in regular movement, either parallel or horizontal. So those may be in the presence of randomized motion. So these particles will be well mixed with this reactor tank. So that is what the sentence meaning. And then suppose this is the concept of mean residence time of the particles or tracer molecules. And suppose one could observe a single molecule. You can observe only a single molecule from the time it is administered into the body. So initially the time will be 0 at the starting point before you are going to administer. So you just administer now, that is at the second of the time will be 0. It will be considered as initial time, that will be 0 until it is eventually eliminated. So this is the starting time and the eliminated time is the ending time. So this is called TEL, that is eliminated time. Here the drug molecules is eliminated out of the body, eliminated out from the body, right? So clearly TEL is not predictable. Why clearly TEL is not predictable? I already told you there is a number of particles involvement is there. So we cannot say that only one particle is eliminated, only 10 particles will be eliminated. So that's why it is a very tough. And one more thing, in some instances your drug molecules will be resided in your body up to the weeks. in case of controlled drug delivery systems. So how many days or weeks it will be stayed, it will be depending upon the dosage form type. Either it may be sustained release or controlled release. So it will be released its drug up to prolonged periods of time. So that is in the mean of months also, weeks to the months. So in such cases, we cannot say that only 10 particles will be eliminated, 12 particles will be eliminated. So that is what the sentence is. We cannot say elimination of the tracer molecules from our body exactly. That's why clearly the TEL elimination time is not predictable. That means the individual molecule could be eliminated during the first minute or could reside in the body for the weeks. If, however, one looks at large number of molecules collectively, their behavior appears much more regular. So all the molecules will have a collective nature. Either they may be resided or they may be eliminated out. So the collective or mean residence time. So the collective or mean residence time of all the molecules in the dose of all, this is the very important, the collective or mean residence time of all the molecules in the dose, which is called as mean residence time. A probability density function, that is f of t, probability density function, which is multiplied by Tm. Tm is the movement, this is the movement, m stands for movement, the t is the time, and integrated over time, which is yields a movement curve. So here there is a need to calculate the time from 0 to infinity. Why? Because we cannot assume that all the particles will get eliminated at one time. So that's why we are taking every time infinity here. So from the initial time to the infinity time, how many particles will get eliminated from the system to calculate it pharmacokinetic parameters. So that's why here we are taking consideration into 0 to infinity time, and then the equation will be, I will tell you the movements, okay, how the movements of the drug will be. This is mu of small m, or m small mth moment is equals integration from 0 to infinity t to the power of m, integration from 0 to infinity t to the power of m, f of t into dt. This is the basic equation to determine the residence time of the movement, that is first movement or 0th movement or second movement of your drug. So where f of t is the probability density function. So it is a mathematical expression of our equation, right? So that is a probability density function, is the time, t is the time, and m is the moment. Either it may be first moment or second moment. See, suppose your m is equal to 0. This is the initial moment. So if you substitute, instead of this Tm, if you substitute this M0 value, you will get an equation like this. Mu of 0 is equals integration from 0 to infinity f of t into dt. Here this whole term will become 0. That's why there is no need to write here. So if the distribution is true probability function, the area under the zero moment curve is 1. See ma'am, here in this statistical movement theory, under this non-compartmental analysis, in this statistical movement theory, we are going to analyze the drug molecules movement in our body. That means it will be totally dependent upon the elimination factor of a drug. So we are taking consideration into the all drug molecules which we are injected. So then we have to take residence time of the drug molecules. We cannot take individual drug molecules time at which point it will get eliminated out. So for that reason, we are taking mean residence time of all the particles. So we are going to calculate different kinds of pharmacokinetic parameters using this phenomenon. So your drug is having some movement between the curves. So how it will be, I will tell you. And then if m is equals to 1, you can substitute instead of writing t to the power of m, here t to the power of 1. Simple. If m is equals to 2, you can substitute t to the power of m. Instead of this t to the power of m, you can write t to the power of 2. So equations will becomes like this. Then the higher movements such as 3 or 4 represent skewness or kurtosis. So when you take your drug molecules movement into consideration, that plot, when you plot a graph between time versus plasma drug concentration, if your drug molecule after entering into your body, immediately it will produce one graph. This is called the first movement curve. So in this first movement curve, only few particles will get out of the body. That is, only few particles will enters into the elimination phenomena. Then the remaining particles are exhibiting one more graph. This is called the second movement of the curve. So that's why the first movement, the second movement, the third movement. In some drugs, in some cases, they used to play 3, 4, they used to give 4 or 5 curves. The meaning is that higher movements such as 3 or 4, it will represent sometimes skewness and kurtosis. What it is, skewness and kurtosis, here two terms are there. You might have studied under probability topic of biostatistics. Skewness is a measure of the degree of frequency of distribution of the particles. And kurtosis is a measure of the degree of tailedness. In case of kurtosis, the graph is like this. So it is looking like a tail. So that's why the name called tailedness in the frequency of distribution. Distribution. This distribution is nothing but your drug particles distribution in your body fluids. That's it. Okay, don't get confused. Here you are going to measure the movement or the residence time of the drug molecules in your body. So while going into movement, that particles will undergo skewness or kurtosis mechanisms because of because it will get sometimes third or fourth movement curves. So in case of skewness, the degree of frequency distribution of the particles may be differentiated. Okay, may be diverted. And conversely, the kurtosis is a measure of the degree. Here we are going to measure the tailedness in the frequency of the drug molecules distribution. So this skewness is an indicator of lack of symmetry. And your curve may be shifted to either right side or left side with irrespective of the central point. See how it will be. In case of skewness, so this is orange color curve represents you. Here you are going to get some peak. So this is the skewness at 0. So with irrespective of this skewness, some drug molecules will show positive skewness, then the curve is shifted to the left side, or the curve is shifted to the right side, it is denoted you as negative skewness. So in some cases, there is a chance to get these two positive and negative skewnesses under the frequency of drug particles distribution. So at this peak skewness, the value becomes 0. And in case of kurtosis, how it will be? I already told you that when you take consideration into the drug particles distribution, you will get some tail-like structure, tail-like peak. So this is called tailed peak. This is the kurtosis peak. So here this graph is representing you the positive kurtosis, and here this is the negative kurtosis. But Where the original normal kurtosis graph? This middle one. So if your particles will distributed in this normal curve, this is normal kurtosis. When your particles will get distributed like this is called negative kurtosis. If you will get peak more height than this normal peak, then you will get the positive kurtosis. So this skewness and kurtosis are the two phenomena which will be describes you the degree of frequency of the particles distribution in our body. So it is totally dependent upon the probability phenomenon. So this is what the skewness and kurtosis. The principal use of movement curve is the calculation of the MRT of a drug in the body, mean residence time of a drug in the body. The elements of the distribution curve will describes you the distribution of drug molecules after administration and the residence time of drug molecules in the body. So the next important one is how you can analyze this mean residence time of drug moiety in your body. There is a non-compartmental approach which is based on the statistical movement theory. So you are injected the particular drug molecules at the constant dose into your body. The molecules will be having some distribution on the basis of statistical movement theory, right? So how you can analyze this mean residence time of that particular drug molecule? This statistical movement theory involves the collection of experimental data following a single dose of the drug. If one considers the time course of the drug concentration, the time course, here the time course is the most important factor in the plasma as a statistical distribution curve, then you can analyze this mean residence time is equals AUMC by AUC. You all know about the AUC. This is area under curve. Previously we studied like this. The area which is available for drug absorption under this curve, we are denoting this is as AUC. This is area under the curve. So this curve was happened here at the zero moment. So that's why this is called area under zero moment curve. That is, this was appears at time zero. This area under zero moment curve was appeared under time zero. After time zero, when you increase the concentration, see, you are able to get one more curve. So this curve is called as area under the first movement curve. So that's why this is called area under the first movement curve, AUMC. So everyone has to remember this equation, MRT is equals to AUMC by AUC. So where you will get this AUMC and AUC? When you take the time from 0 to infinity time, you have an equation previously, T into Ct into dt. And here this curve is traveling along with the time. And in this AUC, this is a zero movement curve. That's why here no time. Directly see T into dt. Here this T is not there. So that is equals, this is what the AUMC and this is the AUC. When you see these equations, previously I show you know, so these equations you know how this time and this dt and this integration from 0 to t, the moment of the curve will be. These equations you get from there. And then this AUMC, thus this area under the first movement curve is obtained from a plot of a product of plasmater concentration and the time, that is C versus T at time T to infinity. Sorry, from T 0 to infinity. So that's why you can take 0 to infinity time. So your equation will be AUMC is integration of 0 to infinity and C t dt. This is the first movement curve is traveled along with the plasma drug concentration along with the time. The time will be from 0 to infinity. So your drug molecules will get transferred from time 0 to infinity. And then in case of AUC, this is the zero moment curve, right? So this AUC is obtained from a plot of plasma drug concentration versus time 0 to infinity. And this is mathematically expressed by this equation. AUC is 0 to infinity C dt. Here no time is there because this AUC was obtained at 0 time. So that's why you cannot consider this t here. Here only c is there. These two equations are similar. Only the difference is in case of AUMC you have a t, and in case of AUC you don't have a t. Okay, so this is the equation, and from this graph, this is the last graph. Okay, so you want to know how the movement of the curves will be. When you take any drug into your body, so it will able to give different curves at different time intervals. Okay, so initially at 0 time, you can initially at time 0 you can able to get area under the curve. At time increases, you can able to get AUMC, and that means area under the first movement curve. This is first movement curve and this is zero movement curve. So here there is a rule that is called trapezoidal rule. So here you may have observed some horizontal lines or vertical lines, and under AUC boxes lines are there. Under AUMC only single lines are there. So what is this? These are time. These are concentration values. So the T1 is respected to the C1 concentration. T2 is with C2. T3 is with C3. T4 is with C4. So these are the different time intervals when you take it on x-axis, and this graph will gives you first zero moment curve, and this graph will gives you the first moment curve. Here where you will attain this peak, where you will attain this peak will be produced at this point, right? Not this point. So from this point you can take consideration into your time as 0. That is, here at this peak point you can consider at t0. Then the next peak you can consider at time t1. The time t1 is respected to the C1 concentration, and the next peak that is T2, that is C2. Next one T3, C3. So same like manner you can consider up to the final elimination stage of all the drug moieties available in your body. So you can able to get n number of concentrations and n number of times. So that's why here you are taking mean values of the time. Okay, so see here how you can calculate this AUC, and see AUC is T2 minus T1. So here we have a T1 value and T2 value. So T2 minus T1, you are going to minus the values. So you are going to minus the values here, and then C1 plus C2. See, suppose this is the time third hour and this is the time fifth hour. So here T2 minus T1 is how much? 2. And then the concentration is adding. Suppose here you are taking 10 microgram per ml and here you are taking 20 microgram per ml. 20 plus 10 is 30 divided by 2. Here you will get one x value. So why we are deleting the time and why we are adding the concentration? See, I already told you the concept like at a time all the particles will not be exited from our system. So there is a time being processed the what is that? The drug particles will get eliminated out. So initially you have taken the drug molecules at time 0, right? So then the time is passing on, that is 3 hours, 5th hour, 6th hour. But we can able to get at the particular time here, we need to minus it. We need to subtract the time here. And then for each and every time, the concentration of the drug is more. Why? Because it is residing in your body for long periods of time. Suppose you can take 1000 microgram or 100 microgram of the drug dose. Okay, so initially only 10 microgram of the drug will get eliminated out, but we cannot predict that total 10 micrograms will get eliminated. No, at least 2 to 3 microgram will be staying inside of our body. So next hour, next to the first hour, that is either 5th hour, again you can eliminate only 10 micrograms. So there is an accumulation means addition of remaining dose. Accumulation means addition of the remaining, that is leaving dose, what have left with the previous time interval. So you can go on adding that concentration. That's why here we are adding the concentration of the drug dose, but we are subtracting the time intervals. So then for likewise we can able to calculate this AUC, area under the curve, how much amount of the drug concentration is available for absorption. Practically, the AUMC and AUC can be calculated from the respective graphs by the trapezoidal rule. So the MRT is defined as the average amount of the time spent by the drug in the body before being eliminated. So before it's eliminated, how much time it will be spent in our body, that time we are going to calculate it out. That is nothing but mean residence time. And then what are the applications of the this movement, this mean residence time? It is widely used to estimate the most important parameters like bioavailability of the drug. Bioavailability means rate and extent of the drug available in our body. So we can able to estimate this bioavailability, and then the clearance and apparent volume of distribution. So here we can able to calculate three different pharmacokinetics, and this method is also useful to determine the T half of first order absorption of the drugs. T half. First order means these are depending upon the concentration. So we can able to find out bioavailability, clearance, apparent volume of distribution, and the first order half-life of a drug. These are the applications and the advantages of these non-compartmental methods. Ease of deviation of pharmacokinetic parameters by single algebraic equations. So without deriving any equations, we will get this pharmacokinetics analysis by using single algebraic equations. And then the method is very simple. The drugs which will follow the first order kinetics, it is applicable to all the types of first order following drugs. And then a detailed description of drug deposition is not required. So it is not requiring the drug deposition. Deposition includes distribution, metabolism, and excretion of the drug. Okay, we may not take consideration into detailed deposition, drug deposition characters. And then what are the disadvantages here? It provides very limited information regarding the plasma drug concentration versus time profile. We already learned this plasma drug concentration versus time profile curve under second unit, right? It provides a very limited information regarding this curve. And then this method always deals with the averages, not for a single molecule. So we are calculating only the average mean time, no? So that's why this method is dealing with averages. So only these two disadvantages are there with this statistical movement theory. So whenever they will ask in your exams, you can write statistical movement theory including the mean residence time. So once the drug molecules will distributed statistically, we can able to determine the mean residence time. These two have to written combinedly. So this is what the today's class, and in the next class I will tell you the remaining part.